Have you ever just, looked around at the world and wondered how it all works? I mean, from the phone you're holding to the chair you're on, everything is built on this kind of invisible architecture. Well, today, we're going to go on a journey deep inside these everyday materials to really uncover their secrets. We're going to peel back the layers and see what's actually holding our world together. So, here's a question for you. Why is a diamond so incredibly hard you can cut glass with it, but the plastic bottle in your fridge is soft and bendy? Well, the answer isn't magic, it's engineering, but on a scale that's almost impossible to wrap your head around. The secret is this hidden architecture, the way materials are put together at the atomic level. And that is exactly what we're going to explore. So here's our game plan. We're going to start with the absolute basics, the little building blocks, and then see how they get put together. We'll check out the glue that holds them, the patterns they form, and then finally, how all of this stuff creates the materials we use every single day, and even how we can invent completely new ones. All right, first things first, we have to start at the very, very beginning. We're talking about the smallest possible unit, the universal Lego bricks that build, well, everything in our world. And that basic unit, it's the atom. This is our starting point. Every single material, doesn't matter if it's metal, wood, or even the air we breathe, it's all formed from atoms. So if you want to understand why a material does what it does, you've got to start right here. And you know what? Every atom just boils down to three simple parts. Right in the center, in the nucleus, you've got your positive protons and your neutral neutrons. And then whizzing around that core are these tiny negative electrons. That's it. This really simple, elegant setup is the blueprint for everything. Okay, so we've got our atoms. The next logical question is, how do they actually come together? And that brings us to the first two major ways we categorize stuff, as either elements or compounds. Now, this is a super important difference. Think of an element like pure gold. It's made of nothing but gold atoms, period. A compound, though, is like your table salt. That's NaCl, right? It's made from two totally different elements, sodium and chlorine, that have been chemically fused together. And this table really shows you just how different they are. We've only got about 118 known elements, the ingredients on the periodic table. But when you start combining them, you can create a number of compounds that's basically endless. But look at that bottom row, because this is the key. You can't break an element down any further with a chemical reaction, but you can break a compound back down into the elements that made it. So we know atoms can join up, but how? I mean, what's the force that's actually holding them together? This brings us to probably the most important part of our whole story, the rules of what I like to call atomic glue, or what scientists call atomic bonding. It turns out there are three main ways that atoms stick together. We're going to look at each one, because the type of bond an atom uses is what really decides a material's most basic properties, like how strong it is or if it can conduct electricity. Okay, this slide right here is huge. In an ionic bond, one atom literally gives an electron away to another. You've got a giver and a taker. You see this a lot in things like ceramics. Then there's covalent bonding, where atoms share their electrons. They're cooperating. This is the super, super strong bond you find in diamonds and also in plastics. And finally, you've got metallic bonds. This is where all the atoms just throw their outer electrons into a giant community pool that they all share. And that free-floating pool of electrons, that's exactly why metals conduct electricity so well. It's not just the bond that matters. It's also the arrangement. Once those atoms are all bonded together, how do they organize themselves in a solid? Well, it's really a story of order versus chaos. I love these analogies because they just make so much sense. A crystalline structure, that's like a disciplined army, with every single atom in a perfect repeating line. That incredible order is what gives stuff like metals and diamonds their strength. An amorphous structure is the total opposite. It's a chaotic crowd at a concert, no pattern, no order at all. Glass is the perfect example of an amorphous solid. So this is where it all comes together. We've got the bonds, that's our glue, and we have the structure, that's the arrangement. With just those two ideas, we can finally understand the secrets of different material families, starting with polymers and ceramics. So let's start with polymers, what we usually just call plastics. They're made of these incredibly long chains of molecules. Now, the atoms inside each chain are held together by those super strong covalent bonds we talked about. But the bonds between the chains are way, way weaker, and this lets the chains kind of slide past each other, which is exactly why plastics are so flexible. Now let's look at ceramics.
They use a mix of ionic and covalent bonds, which are way stronger than the bonds you find in metals. And that strength translates directly to their incredible hardness. Also, notice this. Their electrons are held super tightly in place, and that's why ceramics don't conduct electricity. They're amazing insulators. See? It all goes right back to the bonds.
So understanding these rules is one thing, but what happens when we start using those rules to design materials from scratch? Well, that takes us into the really amazing world of composites. A composite is basically a best of both worlds kind of material. You physically mix two or more different materials, you don't combine them chemically, to create this new blend that has properties neither of the original materials had on their own. It's pretty cool. And the idea behind it is actually really simple. You have the matrix, that's kind of like the glue or the jello holding everything together, and then you stick something else inside it, the reinforcement to give it new powers, usually strength. Think about carbon fiber. You have super strong carbon fibers, that's the reinforcement, stuck inside a polymer resin, that's the matrix. So, at the end of the day, it all comes down to this one simple truth. The hardness of a diamond, the flexibility of plastic, the conductivity of metal, none of it is an accident. It all comes from this unseen architecture. It's not just what a material is made of, it's how its atoms are glued together and arranged in space. And that leaves us with a pretty exciting thought, doesn't it? We've cracked the code. We understand the bonds. We understand the structures. So if we can now consciously pick and choose these properties to design new materials literally from the atom up, just imagine what incredible things we're going to be able to build tomorrow.